Hi everyone, I'm Ben Watson, a hydraulic modeler at Jacobs with 3.5 years of experience working in the water environment industry. As part of my role, I work on hydraulic modeling projects on a daily basis using Flood Modeler for a range of clients, both within the UK and abroad. Today, I would like to talk about some of the common applications for 1D-2D models. I'll then move on to discussing why speed and efficiency matter in flood modeling. I'll present some of the key tools available within Flood Modeler for building 1D-2D flood models. I'll finally move on to a live demonstration where I'll be building a 1D-2D model in just 10 minutes. I'd like to just highlight that today's webinar will focus on the 1D river and 2D surface water solvers within Flood Modeler. However, the 1D Urban Solver is also available within Flood Modeler that allows users to combine surface and subsurface flow to obtain a detailed and integrated understanding of flood risk in urban areas. So firstly, why would we use a linked 1D-2D modeling approach? What are the benefits of doing so, and what are the applications? Well, a 1D-2D modeling approach combines the benefits of 1D and 2D models. This means we can take all of the good parts of a 1D model, such as the ability to include a detailed representation of the river channel, detailed representation of in-channel hydraulic structures, and the ability to model complex operational control features, and we can combine them with all of the benefits provided by 2D modeling, such as having the ability to model multiple flow routes across the floodplain, identify flooding properties and receptors, and it allows the production of 2D flood maps and grids to inform economic appraisals. And by combining these approaches into a linked 1D-2D model, we end up with a model that has a wide range of applications, such as the modeling of fluvial flood mechanisms. So we could use a linked 1D-2D model to improve understanding of the baseline flood risk in an area, identify the onset of flooding, and key locations where flooding originates from. We might already know that the cause of flooding is due to overtopping of the riverbanks, but we don't know where the flooding propagates to once out of channel. Or we may be interested in modeling an engineering solution, such as linear defences, and we want to firstly make sure that the solution is viable in terms of reducing inundation to receptors. So we know there are important and useful applications of linked 1D-2D flood models, but why do we need to be able to build them quickly and efficiently? There are a number of explanations as to why efficiency is critical when building flood models, but the point that comes to the forefront of my mind as a hydraulic modeler in the UK flood risk management industry is that the industry is demanding. Our clients, whether in the UK or abroad, expect us to deliver solutions to them in an efficient manner and to the best possible standard. We need to be able to utilize innovations and automated tools in order to build our models quickly and turn projects around to meet client deadlines and ensure that flood risk management schemes are implemented without delay. Another reason for requiring fast and efficient model building tools is flood forecasting. If a model is being used for flood warnings and forecasting, you don't have time to rely on repetitive manual processes when building or updating your model. You really need a model that's accurate and capable of producing the desired outputs in a short amount of time. Finally, your study area may be extremely large, covering several kilometers, where you simply do not have time to manually enter into data and every part of the model. Flood Modeler's integrated toolbox is the solution. We'll now talk about the tools available within Flood Modeler for building linked 1D-2D models. Flood Modeler contains all the tools needed for streamlining the model build process in an intuitive and user-friendly package, enabling the user to quickly become proficient at building and simulating models for a range of applications. The good thing about building 1D-2D models within Flood Modeler is the integrated GIS user interface, which allows you to create and manipulate shapefiles and topographic data without the need of going to a third-party GIS software. However, any shapefiles you do create within Flood Modeler can be opened and edited in a third-party GIS software. So we'll start with the 1D river build section. Here we have the units that allow us to build a 1D model. When building a 1D model, the most common unit you'll be using here is the river section. The river section unit allows you to include a detailed cross-section of your river channel, including the channel geometry, Manning's End roughness, and chainage along the watercourse. There are multiple ways to bring river cross-sections into your 1D model network. In the demonstration later on in this presentation, we will focus on the import model nodes feature. However, other tools exist, such as the cross-section generator tool, which allows you to create your own river sections using elevations from a DTM dataset. or you can manually generate cross-sections by populating data directly into the river section unit. Flood Modeler also enables you to import cross-section data from third-party software such as HEC-RAS, meaning you can convert your HEC-RAS river network into Flood Modeler and have it linked up to the 1D Urban Solver or 2D Solver within a matter of minutes. We then have the hydrograph units. We use hydrograph units to provide hydrological inflows to our 1D model domain. These can range from a simple flow time boundary, which allow us to enter a time series of inflow data, to more complex hydrological rainfall runoff models, such as the FEH or ReFH units. Finally, we'll move to the downstream boundary units. There are a range of boundary units you can use at the downstream extent of your 1D model domain, and the boundary condition you apply will be dependent on your study. We might want to specify a flow depth relationship at the downstream model extent, and in this case, we'd have two options. The first being the Flowhead unit, where you would directly input your flow stage data. So maybe you've truncated your model and you already have this data available. The second is the normal depth boundary, whereby Flood Modeler would automatically generate the flow depth relationship based on the bed slope, water surface slope, or a manually entered slope. You may want to specify a head time boundary. This is most commonly used to apply a water level time series at the downstream model extent, such as when your model domain is truncated at the confluence with a major watercourse, and you want to simulate the impact of the water level in the major watercourse on your model domain. Other options include a tidal boundary if a tidal influence on your river channel is something that needs to be investigated. So once we've constructed our 1D model domain, in this case, it would be made up of a series of river sections with an inflow hydrograph at the upstream extent and a 1D boundary condition at the downstream extent. We can then go on to building the 2D domain of the model. Firstly, we can specify our 2D model domain using the active area tool. This will allow us to generate a new shapefile and create a polygon covering our area of interest within the floodplain. Flood Modeler calculates the output variables that you specify, such as depth, elevation, flow, and velocity for the area bounded by the active area. If the active area shapefile is not specified, then Flood Modeler will calculate the variables for the whole 2D computational area, which may lead to significantly longer simulation runtimes. Active areas are defined by a polygon shapefile. Flood Modeler only requires the geographic information contained within the shapefile, therefore it doesn't matter what attributes are assigned to the shape. It's also worth mentioning that if you need to model multiple sections of a floodplain and each area requires a different grid resolution, we can incorporate multiple active areas into a single 2D simulation without compromising model performance. Next, we have the link line generator tool. This tool allows us to create a boundary condition between the 1D and 2D model domains. The link line generator tool does this in an automated way by using the 1D model network and 2D active area to automatically digitize the boundary line between the two. While creating a link line, we have three options for specifying the type. A level link, this is where the 1D domain sends water level information to the 2D and the 2D sends flow information back. A flow link is where the 1D model calculates how much flow is exiting the 1D domain and the 2D returns calculated water level information. And finally, a weir link. Within this option, the 2D solver calculates flow over the boundary using standard weir equations, and the 1D domain returns water level information. Finally, we have a few GIS tools that provide some additional functionality in Flood Modeler when building 1D-2D models. The first is the Extend Cross-Section tool. This allows us to extend our 1D cross-sections. We might use this in cases where there's a localized low point in the floodplain or where water is expected to exit the channel and immediately re-enter, resulting in recirculation. Once extended, we can then use the Set Missing Z option to populate elevations within the extended points of the cross-sections using DTM data. Finally, we have the layer editor tools. These tools become available once you have begun editing a layer within Flood Modeler. These tools allow you to manipulate, edit, and view attributes of shapefiles within Flood Modeler. I'll now talk through how to set up a linked 1D-2D simulation before we look at a live demonstration. A 1D model simulation is defined by a simulation file. For 1D models, this is a text file with an IEF file extension. Within a 1D model simulation file, we can specify the following inputs: our model network, our initial conditions, an event file, which would be a text file with an IED extension, and our 1D model time step, as well as several other options and additional outputs that are discussed in detail on the Fluid Modeler website. We have the ability to run several types of simulations within Fluid Modeler. The steady state solver provides both direct steady state and pseudo time stepping methods to optimize runtime and enhance model stability. It is most often used to obtain an estimate of the initial conditions for your model. However, there are specific situations where steady state simulations alone are appropriate for obtaining model results. The unsteady state solver uses the Priestman implicit scheme to solve the equations for free surface flow based on the St. Bennett equations for flow in open channels. This solver provides various features which have been specifically designed to improve model performance and management capabilities. The unsteady state solver allows the model to estimate stage, flow, and velocity through time along the river channel throughout your simulation. A 2D model simulation is defined within a separate simulation file. For 2D models, this is a text file with an XML file extension. Within a 2D model simulation file, we can specify the following inputs: topographic data, such as our LiDAR digital elevation model, specify ground elevations within our 2D domain, topographic features such as bunds, walls, or buildings, spatially varying Manning's-N roughness throughout the 2D domain, which can be informed by data such as OS master map, input boundary conditions, so here we might have inflows applied directly to our 2D domain, and we can also link to our 1D simulation file that we've already created for our 1D river model domain. It's also worth noting that when running our 2D model, we have the following options for multiple 2D solvers: the ADI solver, which stands for alternating direct implicit, the TVD solver, which stands for total variation diminishing, and the fast solver. Additionally, Fluid Modeler now contains the option to run your simulation with GPU, which is based on the TVD-2D solver and runs up to 94% faster depending on your hardware and model configuration. For the purposes of this webinar, we will focus on the ADI solver, but more information of the available 1D and 2D solvers are provided on the Fluid Modeler website. Okay, so I'm now going to move over to Fluid Modeler to provide a demonstration on how to put all of that information together and build a 1D, 2D model in just 10 minutes. So I'm starting here with a completely blank workspace within Fluid Modeler, and just to show that it really can be done in 10 minutes, I'm going to start a 10-minute timer. So I'll first add some background mapping just to provide some geographical context to our model. So I'll navigate to the base map drop-down menu and select OpenStreetMap. So to build the model, I'll first import some topographic data. In this case, I'll be using a 2-meter resolution digital elevation model. Once loaded, we have the ability to change the color ramp of the DEM, where we have a range of predefined color ramps available, and I'm going to select the terrain with hill shading. We're then going to create a new 1D river network. I'm going to call this Upturn 1D. This is a blank river network, so we'll need to import some data into the model. To do so, we'll move over to the network window, right-click, File, and Import Model Nodes. In this scenario, I'm being provided survey of all channel cross sections in a section or .sec file. And we're just going to select all of those and drag them across into our network window and click Save. So you can see there that all the sections have been brought into our network. We'll now create some inflows to the 1D model domain. So we'll go to the upstream model extent and import an inflow hydrograph in the form of a QT boundary. So I'm being provided with an inflow unit from the hydrologists. So I'm just going to navigate to that inflow data. Select the IED, and again, drag across into the network window. We'll click yes to link to the upstream node. And then I'll just show the populated QT boundary. and our inflow hydrograph there. Now we'll create a downstream boundary condition. So we'll go to the downstream model extent, and we're going to import a flowhead condition from an IED file. So in this case, the model is truncated, and we've got some extracted results from a larger model at this location. So again, I'll just navigate to the data, select the IED, drag across into the network window, and click yes to link to the downstream node. And there's our populated flow stage data at our downstream extent. Now that we've created our model, we need to create a 1D simulation file to produce some initial conditions. So we'll go to simulations, right click and select new 1D simulation. I'm going to call this upturn 1D steady. We'll firstly check that we're reading the correct DAT file and that the results are being output to the correct location. We'll stick with the default settings on the steady direct simulation and we'll click run. Okay, so once we've got our steady simulation, we have our initial conditions, we can then go ahead and create an unsteady simulation. So again, we'll do one new 1D simulation. We'll call this upturn 1D unsteady. Make sure we've got the correct DAT file. Again, check that the results are being output to the correct location. And this time, we're just going to choose an initial conditions file, and we'll navigate to the steady results that we just created. In the times tab, we'll select unsteady fixed time step. I'll go with the time step of 2.5 seconds. We're going to go with a finish time of 30 hours, and we'll run that. So the simulation window here is going to provide us with real-time model performance indicators as the simulation progresses, and we'll get a log output throughout our simulation. So I'm just going to leave that running in the background, and I'll go ahead and start on the 2D model domain. So I'm going to start by dragging in our 1D river cross sections to visualize the extent of the 1D model. Once done, I'll start with creating the active area. So we'll go to 2D build, active area. I'll call this active area. And we're going to use the polygon tool. We'll set the snapping to snap to the endpoints of the cross sections. And we're just going to snap along the right bank of the channel to create our active area. Okay, so once we've got our active area, we'll click save. We then need to use the link line generator tool to create a 1D-2D link along our 1D and 2D model domains. So firstly, we want to make sure that we've got the 1D cross-section labels on. We'll then use the link line generator, and we'll populate the tool with the necessary inputs, starting with the DAT file, our upstream and downstream model nodes. So I'll just populate those now. We'll select right bank, we'll trace along the active area, we'll import our data from the DEM. We'll stick with a level link, and we're going to create a new shapefile, call this link line. And then if I just turn the active area off there, you can see that we've got a nice link line generated along the right bank of the channel. We can now go ahead and create the 2D simulation file. So again, we're going to right click, new 2D simulation. We'll call this upturn 2D. And we can populate the 2D simulation file starting with the general tab. So we'll link to the 1D river model. We'll match our end time of 30 hours. We'll bring in our topography data. Grid size, we'll go for 20 meters. 10-second time step. Drag in the active area. Stick with the default of 0.1 on the roughness, but you can add your spatially varying data such as OS master map here. We'll bring in our unsteady simulation. drag in the link line to link the 1D, 2D model domains, click Save and Run. Okay, so you can see how easy it is to build a 1D, 2D model in under 10 minutes. We've got about a minute remaining, so I'm just going to stop the timer there. Similarly to the 1D unsteady simulation, the 2D simulation window provides us with real-time model performance indicators for both the 1D and 2D model domains, as well as the log output throughout our simulation. So I'll just wait for that simulation to quickly finish. And once finished, we can then load the results into the Fluid Modeler map window. So we'll do so by closing down the simulation files, go to our simulation here, right click and view results. Here we get the option to show all time steps or just the max values. And for this example, I'm just going to go for the maximum. So I'll click OK. And then if I turn off the active area, you can see there we're showing maximum flood depths in the floodplain, as well as the maximum velocity vectors. Similarly, for the 1D, if we wanted to show a cross section, so we can select one of our river sections, go to results, cross section, and here we're going to show stage, maximum stage, bed elevation, and click plot. So you can see we've got the maximum stage here, the initial stage, and if I just turn the animation on, we can see how the stage progresses throughout the simulation. And that's everything for the demonstration.